Very good day to everybody. This is electromagnetic fields and waveguides. This is the practical session, and in today's class we'll discuss about standing waves and of course resonance. Okay, so this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. So in this class, we'll discuss about standing waves and of course resonance, how the incident wave will be reflecting off the end of the unterminated transmission line. So we already know about incident waves, we already know about reflected waves. So in this class, we'll understand the sum of the incident waves and reflected waves is a stationary wave. Okay. Then we'll understand how the stationary wave or maybe the standing wave does not propagate along the transmission line. Okay, so we'll understand what are the cases where the standing wave is actually produced. Then we'll have an experiment about plucked string and shaken string. Okay, we'll understand the phenomena of the standing sound waves in the open-ended tubes, and we'll understand the progression of harmonics of the resonant frequencies. So finally, we are going to end this class with the simulation of the transmission line resonance using the SPICE platform. Right. So at regular intervals, I'll be giving you some short videos to discuss the knowledge in your topics. Right. So standing waves and of course resonance. So we in the previous classes we saw the matched impedance phenomena. So whenever there is a mismatch of impedance between transmission line and of course load, you will have reflections. So maybe if the incident signal is a continuous AC waveform, the reflections will be mixing more of the incoming incident waveform in order to produce the stationary waves, what you call to be standing waves. Okay, so we'll see a triangular shape structure, okay, incident waveform that will have into a mirror image reflection on reaching the line's unterminated end. Okay, so the transmission line, it's a single thick line rather than a pair of wires for the simple case. Okay, so the incident wave, it will be traveling from left to right, while reflected wave will be traveling from right to left. That was what we can see here. This is the direction of propagation for the unterminated line. Okay, so we'll see a bigger waveform and reflected wave taking in the opposite direction. So incident wave is going to reflect off the end of the unterminated transmission line. So this is again the incident wave which is going to reflect off the end of the unterminated transmission line. Here the reflected wave is going to take the direction in the opposite direction. Okay, so that is going to construct across the wave. This is where it is going to join across the length of the wave. Okay, so you see the pattern, which is actually it is joining, then again it is constructing, joining the second end. Okay, and it is propagating along the line. Okay, so that construction part we are going to see here. So see here this reflected wave taking the maximum wave. Okay, so we see across the incident wave we can see reflected wave also. So at the ends where incident wave is projected, reflected wave is going to join. Okay, right. So maybe as I told you, if we try to add these two waves, incident wave and reflected wave, we will be getting a stationary wave, what you call to be the standing wave. Okay, so the standing wave is created along the line's length. Okay, so as I told you, when the source and when the wave is actually propagated, it's actually terminated in an unterminated line, we get the reflected wave, and this is the sum of the wave. So the sum of the incident wave and reflected wave, as I told you, it's a stationary wave. Incident wave in the green color, reflected wave in the blue color, and red color is nothing but the sum of the waves. Okay, that red color. Okay, so the sum of the incident and reflected waves, it's a stationary wave called as the standing wave. Okay, right. So this is the projection. So as the wave is going to travel, you are going to make the sum of the two waves. Okay, that's what I told you. If you have studied signal system, this would be much easier. Okay, because we will be adding the signal, we will be subtracting the signal, multiplying the signal, dividing the signal, phase shift of the signal. For example, one signal in the opposite direction, phase shift, opposite direction. So we will be doing plenty more with the waves. Okay, so this is what we are going to actually project it. Okay, the total of the incident and reflected waves. the total wave will be adding, and it will be it will be acting as the reference signal between the incident as well as the reflected waves. So you can see that sum will be on the line. Okay. So this is the third standing wave that will be representing only voltage across the line, that is the sum of the incident as well as the reflected voltage waves. So it is going to oscillate in the instantaneous magnitude, but it will not be propagating down the cable length like the incident or maybe reflected waveforms. Okay, so we see here dot. Okay, so that it is going to mark the 0 point across the incident as well as the reflected wave, which will be cancelling each other. Okay, but however the points will not be changing the position. Okay, so this is the standing wave. Standing wave, it is propagating, but it will be standing still. Okay, it will not be propagating along the transmission line, will not be moving. It will be standing still, but it's a wave. Okay. So these are the cases where a standing wave will be produced. We already saw this example. Okay, so consider a string or maybe rope shaken at one end, but the other end is actually tied. Okay, so only one half of the cycle of the hand motion is being shown, so that will be moving downward. It will be forming a wave, and then it will subside. The line will be straight. Okay, so here you see the wave being generated with the standing waves on the rope. Okay, so it is still only. Okay. So both the nodes, as we saw, points of little or maybe no vibration, and maybe antinode, which is nothing but maximum amplitude, will be remaining fixed along the length of the string or maybe rope. It is not different, it will be fixed. Okay, so the effect is more pronounced when the free end is actually shaken at the same frequency, at the right frequency. So this is where we have the plucked string. Okay, so that will be having the standing wave behavior with the nodes of maximum as well as minimum vibration across the length. Okay, so major difference between the plucked string and maybe shaken string is that plucked string will be supplying the correct frequency of vibration in order to maximize, improvise the standing wave or maybe stationary wave effect. Okay, so this is the plucked string. Okay, will have the propagation. Okay, so when the wind blowing across the open-ended tube also produces standing waves. So the waves are nothing but vibrations of the air molecules that can be compared with the sound within the tube rather than vibration of a solid object. So whether the standing wave is going to terminate in the minimum amplitude, what you call to be node, or maybe maximum amplitude, what you call to be antinode, depends on whether the other end of the tube is maybe open or maybe closed. So we'll see over here. This is quarter wave, then quarter plus quarter, that is half. Half plus quarter, 3/4. 3/4 plus 1/4, 1. 1 plus 1/4, 5/4. 5/4. 1 plus 1/4 equal to 5/4. 5/4 plus 1/4 equal to 6/4, which is nothing but 3/2. Then 3/2 plus 1/4, you get 7/4. 7/4 plus 1/4 equal to 8/4 equal to 2. 2 plus 1/4 equal to 9/4. And 9/4 plus 1/4 equal to 10/4, which is 5/2. So for each of the thing we will be seeing the waveforms. Okay, so quarter means it will be very big.
Quarter is very big.
Then no, for the big, the wave would be big like this. And after that half, okay, little small. 3/4, okay, it is getting small. One wave, for this wave you will be getting projection like this. Then 5/4, see here, this one. Then 3/2, yes, this one. Okay, then 7/4, even small. 2 wave, small. 9/4, even small. 5/2, even small. Okay, so the closed tube must be the wave node, while the open end must be an antinode. So antinode, it's maximum amplitude. Antinode means maximum amplitude. Node means minimum amplitude. Okay, so the anchored end of the vibrating string must be a node, while the free end would be a antinode. Okay. So we see that there is more than one wavelength suitable for producing the standing waves of vibrating air within the tube that precisely is going to match the tube's endpoints. So this is actually true for all of the standing wave systems. So standing waves will be resonating with the system for any particular frequency or wavelength correlating to that particular node or maybe anti-node points of the system. So we can say that there are multiple resonant frequencies for any of the system which is going to support the standing waves. Okay. So these you saw, okay, resonant frequency, it's okay. Higher frequencies will be integer multiples of the basic or maybe lowest fundamental frequency for the system. So the sequential progression of harmonics from one resonant frequency to the next will be defining the overtone frequencies for the particular system. Okay, so we saw here, okay, we already saw this one, but these are the harmonics or maybe overtones in the open-ended pipes. Okay, so quarter, half, 3/4, 1, 5/4, 3/2, 7/4, 2, 9/4, 5/2. So first harmonic, second, third, fourth and fifth harmonic. Here you see first harmonic, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic. This is all from here. 1, 3, 5, 7, 9. Okay, right. So this is first overtone. This is actually basic, fundamental, first, second, third and fourth overtone. Okay, so depending on whether it is open or closed. Okay. So the actual frequency is what you are going to measure in hertz for any of the harmonics or maybe overtones depends on the physical length of the tube and of course the wave's propagation velocity, which is nothing but the speed of the sound in air. Okay. So we can also simulate this using SPICE platform also. Okay, so because transmission line is going to support standing waves and of course force these waves in order to possess nodes as well as antinodes according to the type of the termination impedance at the load end. They will be having, you know, the resonance at the frequencies determined by the physical length and of course the propagation velocity. So transmission line resonance, of course, it's more complex than the resonance of maybe strings or maybe as in tubes, but we consider both the voltage waves as well as the current waves. Okay. So the complexity, of course, it's much more easier to understand when you try to simulate it using the SPICE platform. Okay. So let us consider an example. We'll examine a perfectly matched source, a transmission line and of course load. Okay. So here you see the source voltage, source impedance 75 ohm, transmission line impedance of 75 ohm. We have the load to be 75 ohm. Okay, so using the simulation software SPICE, we'll try to specify a transmission line T1 with a 75 ohm characteristic impedance, which means Z0 is equal to 75 ohm and maybe propagation delay of 1 microsecond. Okay. So this is actually how you specify the physical length of the transmission line, that is the amount is taken by the wave to propagate down the entire length. Okay. So let us take in the case if it's a real 75 ohm cable. So there would be, we will be using this RG59B/U coaxial cable type. That is actually most commonly used one for the cable TV distribution, that will be having, you know, a common velocity factor of 0.66, what we discussed in the earlier classes. That is approximately 648 feet long. Okay, so we already saw the propagation delay is actually 1 microsecond. Okay, so since 1 microsecond is actually the period for the 1 megahertz signal, we can choose to sweep this frequency of the AC source from nearly 0 to that particular amount what you are going to expose that signals from the DC to the one wavelength. Okay, so this is the SPICE platform. You can place onto elements, okay, the source, the gate voltage, impedance, you can have input current, you can actually measure the reflection coefficient, you can measure, okay, the input impedance. So we'll specify all these parameters and you can specify the conditions for the perfectly matched transmission line.